So, hi everyone, welcome to this week 5 live session. So, we'll just wait for a couple of minutes and then I think we can start. So, I think we can start. We'll start by 3-5, but I think I can give my intro till then and then we can proceed to the problem section. Just a second, just a second. Okay, now let me just share my screen and then we can start. So, so I welcome you all to this live session 5 of the course Digital Circuits. Today we'll be dealing problems related to week 5 material mainly based on multiplexers, logical operators, logical function operation using multiplexers, encoders, decoders and all. So let me just give my introduction first quickly. My name is Musab Rafiq. I'm a PhD student at the Department of Electrical Engineering at IIT Kanpur. And this course is taught by Professor Shantanu Chattopadhyay. So let me just spell out some instructions. Kindly mute your microphone. In case of any doubts, as the audience is quite low this time, you can use your microphone or even you can use the chat box, whatever will be feasible for you guys. But only after problem is solved, it will be better if you ask your problems at the end, at the problem at the end after I solve a problem. I'll give you some time to ask in your doubts. That's not an issue. So let me just go to the first question of today's live session. By the way, am I audible? Can someone confirm? Okay, thank you. So this is the first question of today's live session. So in the following circuit, X is given by, so we need to find out the X that is the output of the following circuit. Given ABC are your inputs that act as the select lines to these muxes. These are the 4:2 1 mux. 4:1, two 4:1 muxes are connected, and we need to find out the final output expression of for X. So how will we do it? So let me just first write down the general expression for a 4:1 mux. So I have a 4:1 mux. So 4:1 mux, as you all know, has four inputs, one output, and two select lines, right? So the select lines are S1 and S0, right? And your inputs are input connections, these pins. You can call it an input pins as well. I0, I1, I2, and I3, right? And based on the combination of select lines, one of the input is passed to the output, right? That is basically your mux. So your output, general output, I'm just speaking of general. So output of mux 4:1 mux is given by S1 complement S0 complement. So I'll call this complement as bar. So you people can infer this by bar. I mean this complement. S1 bar S0 bar I0. So that means when S1 S0 is 0 0, I0 will be selected. Then S1 bar S0 means when select line is 1, I1 will be selected. When select line is, sorry, this is not bar. When select line is 2, I2 will be selected. And when select line is 3, I3 will be selected. So this is your general expression for your 4:1 mux. So what we have here is we have this mux 1. Let me just call it this as 1 and mux 2. Here is your output y. Let me just call it as y1 and x is your y2. So x is x only. So let me just first write the output y1. So based on this equation, we can write y1 as s1 bar s0 bar I0 plus s1 s0 s1 bar I1 plus s1 s0 bar I2 and finally s1 s0 I3, right? So here what we have is s1 s0 as AB. So here s1 is equal to A and S0 is equal to B. This is for mux 1, right? So Y1 will be equal to S1, this S1 is simply A bar, B bar I0 plus A bar, B I1, then AB bar I2, and finally A, B, I3, right? Now what we have here is I0 and I3 equal to 0, right? So I0 is connected to ground and I3 is also connected to ground. So I0 equal to I3 equal to 0 and also I1 equal to I2 equal to 1, as you can see here 1. So my final expression for Y1 will reduce to this term and this term will vanish. Only two terms will remain. So it will be A bar B plus AB bar. So as you can see, using this 4:1 mux, we were able to construct this expression A bar B plus AB bar. And if you people remember, this is simply an expression for XOR gate. Now this Y1 is a select line to mux 2 S1. So X will be equal to same expression. So this expression I'll write here again, just some repetition. I2 and finally S1 S0 I2. So what we have here is I1, I2 equal to 1 and I0, I3 equal to 0, just like the previous case. And S1 is equal to Y1 and S0 equal to C. So let me just write. So we have Y1 bar C bar, that is 0. So let's not write this. This is Y bar C plus YC bar, and the final term is also 0, right? Now write the expression here. So y is equal to, so x is equal to, y is equal to a bar b plus ab bar, and then the whole complement times c, and then a bar b plus ab bar times c bar. Now this is a bar b plus ab bar whole complement. So XOR's complement is XNOR. So I can simply write x is equal to ab plus a bar b bar. So x is equal to ab plus a bar b bar times c plus, and let's just write them together, a bar b c bar plus a b bar c bar, a b bar c bar, and finally my x will be a b c plus a b bar c plus a bar b c bar plus a bar b c bar plus a b bar c bar. And if you carefully look at this, this is expression A. So option A b bar c bar is this, a bar b c is this, a bar b bar c is this, and a b c is this. So option A is the right answer to this question. So any doubts in this question? If there are any doubts regarding this question, yeah, you can ask. Was it clear? So I assume there are no doubts. In case you get any doubts later on, you can ask me anytime. So now let's move forward to question number 2 of today's live session. It states that in a multiplexer, if there are 4 input lines and 1 output line, so it is a 4:1 mux, then the number of select lines will be, so it's a pretty simple question. You saw it in the previous question as well. There were two 4:1 mux and two select lines were there. So simply the answer to this question is 2. So but if you need to find, you have, so generally we write 2 raised to power n is to 1 mux. So whenever you have a mux, so its general form is 2 raised to power n is to 1 mux. So this 2 raised to power n, where n is your select lines. So select lines. Here 2 raised to power n, we have 4:1 mux. So here 2 raised to power n, these are your inputs, number of inputs, simply 2 raised to power n. So here 2 raised to power n is equal to 4, that implies n is equal to 2. This is a simple way of doing it. So n is equal to 2 is your right answer. Now towards the question number 3. So I would like you guys to do this question first. Then I will show you the solution. You people might be aware that I give some questions first to you guys. Then I show the solution. In this way, we can make this live session more interactive. So we have a 3:8 decoder shown in the figure. So we need to find out f of x2, x1, x0. So this is your figure. You need to find out the output. So you have 5 minutes. Please solve this question. And whenever you are ready with your answer, you can type it with your correct option that you have solved. And then I will show the solution. Some of you have written your answer. That's nice. Let's see. So to the new participant that has joined, this is the question. I would like you guys to solve it first, and then I will show the solution. You have 2 to 3 minutes now left. So the question states a 3:8 decoder is shown in the figure. Find f of x2, x1, x0. So when you have solved it, please type in your answer. So has anyone else solved it? It's a pretty simple question. I expected more answers from you guys. So now let me just show you the solution. Okay, let's wait for 1 more minute and then I can show the solution. So let me just show the solution. Before I go for the solution, I'll just say one thing to you guys. This is an advice from myself. Whenever you are appearing for any competitive exams or any exams which involve multiple choice questions, because we usually tend to make these mistakes in MCQs, try to look at question at least twice and see the options, all the options as well. So if you quickly look at this question, you'll just say outline output pins D1, D4, D7 are connected to gate. So 1, 2, 1, 3, 1. So what is it? 147 will be your answer. Min terms 147. But if you carefully examine the output, the gate that is connected at the output is not an OR gate, it's a NOR gate. So 147, which seems to be a simple answer, and is not the correct answer to this question. So it's my advice, always look question twice, always read the question twice, always examine the figure twice. So it is a NOR gate that was at the output, not the OR gate. So the option A, which some of you have written, is the incorrect answer. So now it's quite easy to say it's option B. Now let's just say, now let's show the solution completely, how it's B. So that's why I kept it this question here, because we usually tend to make these kind of mistakes in multiple choice questions or something else. So our output F is simply equal to, so it is D1 plus D4 plus D7, right? D1 plus D4 plus D7. If it was OR gate, it would simply have been summation of minterms 147. But it's a complement to this, so F is equal to, I'm showing the elaborative way, but if you simply, when it's a complement of this, it simply means this. But I'll show you the complete solution here. So it means D bar, D4 bar, and D7 bar, right? De Morgan's law. So then F is equal to this A bar, B bar, C whole bar. Then it's A, B bar, C whole bar. Then it's A, B, C whole bar, right? So this is equal to F is equal to, it will be A plus B plus C bar. Then it will be A bar plus B plus C, and it will be finally A bar plus B bar plus C bar. F will be equal to product of max terms. So this is what it is. This will be 0 0, it will be 1, this will be 4, and this will be 7, and in min terms it will be 0 2 3 5 and 6. So option B is your right answer. If it was product of max terms 147, it would be right. So 147 would be product of max terms, 0 2 3 5 6 will be sum of products. So option B is your right answer. Any doubts? If not, let's move forward to the next question of today's live session. It states that the function f of a1, a2, a3, that is f, is equal to the options that are given. So before we proceed, a 2 is to 1 mux, let's draw here, a 2 is to 1 mux has two input lines, I0, I1, one select line S and one output Y, and Y is given by S bar I0 plus S I1. So when S is equal to 0, I0 will be selected, when S is equal to 1, I1 will be selected. So then my F here will be equal to, so before we go for F, let's just find out these things. So this is x1, I will call it as x1, and this I will call it as x2. So F will be equal to x1 times a1 bar plus x2 times a1, right? And my x1 is simply equal to AND operation between a2 and a3, and my x2 is simply equal to OR operation between a2 and a3. So a2 plus a3, right? So this is and this is OR. Now my F will be equal to x1 is a2 a3 times a1 bar, right? Then OR. So x2, now I'll plug this value of x2 here, a2 plus a3 times a1. So F is equal to a2 a3 a1 bar, right, plus a2 a1 plus a3 a1. So we have to minimize it. As you can see, options only have two letters in these terms. As you can see, 2 2 2 2 2 2. So we have to see if we can minimize it. So the common term that is between these two terms is a2. So inside we will have a3 a1 bar plus a1 times a3 plus a3 a1, right? And here you have a1 plus a1 bar times a3. So you know this property, right? From your earlier weeks you have seen a plus b bar c is equal to, sorry, a plus a bar c is equal to a plus c. So this will be equal to a1 plus a3 simply. So f will be equal to a2 times a1 plus a3 plus a3 a1. So that is equal to a1 a2 plus a2 a3 plus a3 a1, and that is option A, a1 a2 a2 a3 a3 a1. First and second, second and third, third and first, first and second, second and third, third and first. So option A is the right answer. So what we did here is we wrote the expression, output expression for our 2 is to 1 mux. So that is here S bar I0 plus S I1. Then I termed these two inputs as x1 and x2, and I found that x1 was equal to AND operation between a2 and a3, and x2 was equal to a2 plus a3. Then I plugged those values in this expression, and I got this, and I took then a2 common, and I got my final expression as a1 a2 plus a2 a3 plus a3 a1. So any doubts in this question? So that's nice. Now let's move forward to the okay, fine. So now let's move forward to what should I say? Question number 5 of today's live session. So it states that addition of 96 and 69 in BCD is, so we have two decimal numbers 96 and 69, and we need to find their addition in BCD, that is binary coded decimal or 8421 encoding. So 96 and 69, what we'll do first, we'll convert 96 into BCD number, its equivalent BCD number, and then 69 into its equivalent BCD number, then add those two numbers and finally write down the answer. So first let's just write 96 BCD. So here I'll write BCD. So 6, 8421 encoding of 6 is simply 4 plus 2, that is 0, 1, 1, 0. 6 is written as 0, 1, 0, and 9 will be 8 plus 1. So everything need to be written in individual decimal digits, individual decimal needs to be written in 8421 encoding. So 1, 0, 0, 1. This is your 9 and this is your 6. Similarly, since number 69 in BCD will be equal to 6, I have already shown 0, 1, 1, 0, and 9 as 1, 0, 0, 1. Now in BCD addition, we'll add them. And there is a one thing in BCD addition, if the sum comes out to be greater than 10, greater than or equal to 10, so then we have to add 6 to the number. So what we'll do, here we have the number, we'll add them. So we have 1, 1, 1, 1, and here we have 1, 1, 1, 1. So both of them are greater than 10. So we will just add 0, 1, 1, 0 to each term. 0, 1, 1, 0. That is 6 will be added to each term. 0, 1, 1, 0 will be added to each term. So we'll have 1. 1 plus 1 is 2, so that is 0, 1. 1 will be carry. 1 plus 1 is 3, so 1, 1 will be carry. 1 plus 1 is 2, so it will be 0, and 1 will be carry. 1 plus 1 is 2, so 1 will be carry. So 1 plus 1 is 1, so 1 will be carry. 1 plus 1 is 1, 1 will be carry. And 1 plus 1 is 1, 0, so it will be 1. So 1, 0, 1, 1, 0, 0, 1, 0, 1. 1, 0, 1, 1, 0, 0, 1, 0, 1. So option C. So that is 1, 6, 1, 6, then 5, 1, 6, 5. So in decimal, it's 165. So if you can convert it into decimal, this number, this is 165. And if you add the number 96 in 69, it's 5 and it's 165. So another way, what you would have done, you could have converted the number, you could have directly found the addition result in decimal and then converted the result into BCD. But since it was showing this addition of 96 and 69 in BCD, so whole process I wanted to show in BCD because this step is a crucial step here. So main step in fact here. So the result was 10110 0101. So a person has written an option A. I hope that doubt got cleared because that's a normal addition, binary addition that you have done. But in BCD, if the number addition result is greater than 10, so we add 6 to the number. Right? I hope that doubt got cleared. So now let's move for any other doubts. Subtraction will be same result will be followed. Binary subtract, but I need to check. I haven't checked it, so I'll just check it and let you know in the next class because I'm not sure. I haven't done a subtraction, but I'll just come to it. But I guess same thing will be followed. Mm, let me just check and come back to you. I haven't done it, so I can't be sure about that. So now let's just do question number 6. So I would like you guys to do this question first, then I'll show you the solution. It will take hardly 3 to 4 minutes. So the logic function implemented by the multiplexer circuit is, so you have to find out the f of the following circuit, so output of the following circuit, where ground implies logic 0, that is 0. So you need to find the answer to this question. I'll just give you 3 4 minutes and then I'll show you the solution. So I see some of you have solved it. So I was just looking for this BC subtraction. So there are 2 3 methods. One of the method is ones complement method, where you take the ones complement of this subtrahend. So let's just say subtrahend means the number you have to want to subtract from another number. So you take the ones complement, then add up. If there are addition, if there is a carry to the result between the 4 bits of the as if there is a carry, that carry will be added, and finally if the we have a carry at the end, that will be ignored. So I will show in the next class. I will show that if I get time, I'll just show in the next class. Right now I don't have a question for that. In the next class I'll try to show it. So now some of you have solved this question. So let me just show the solution. In fact, there are other methods also, nice complement method and tens complement method, but I think one's complement method will be easy for you guys to look at. And other way is simply just take the subtraction in decimal and write down the binary BCD. But if you want an elaborative, so what we'll do, take the ones complement of subtrahend, add it to the where you wanted to subtract it from, and then if the 4 plus 4 addition gave you an carry, add that to this only. What I mean to say, so let me just show that part. So let's just say if you have, for example, I have one example here, 0001 and 1001, you are adding them, so it will be 1 plus 1 is 0, 1 will be carry. So 1 plus 1 is no, this is not the right way. Yeah, 00010000. Let me just show you the next time. Actually, I myself have some doubts regarding it. So let me just show you the next time. So now towards the question number 6, as some of you have already solved it. So we have 4 is to 1 marks here, and the output, as I already showed you previously, can be written as S0, so S1 S0 bar bar I0 plus S1 S0 I1 plus S1 S0 I2 plus S1 S0 I3. So here F will be equal to, your S1 is equal to P and S0 is equal to Q, so it will be P bar Q bar I0 plus P bar Q I1 plus PQ bar I2 plus P bar Q I3. Now your I0, so this is 0. After NOT gate it will be 1, and after again a NOT gate it will be 0. Your I1 is 1, your I2 is 1, your I3 is 0. Right, 0 1 1 0. You saw this type of configuration previously. It simply is an XOR gate, but let me just show. First time will be 0, second will be P bar Q, third will be PQ bar, as I1 I2 are 1, and fourth will be 0. So F will simply be equal to P bar Q plus PQ bar, that is XOR operation between P and Q. Option D. Now towards question number 7, that is, how many 2 is to 4 decoders are required to implement 4 is to 16 decoder? So you need to find out how many 4 is to 1, 2 is to 4 decoders are required to implement 4 is to 16 decoder. To simply write down the answer, I think you can write it this way. I'm not sure, but I think you can write it this way. So you have M cross N, and you want to make M1 cross N1, and you want to make something like M2 cross N2 decoder in terms of decoders. So you will write N2 by N1 equal to K1, then K1 by N1, that will be equal to K2, so on until this is equal to 1 or 0. So here you have 16 by 4, that is 4, and your number of decoders will be summation of these KIs. So 16 by 4 is 4, then 4 by 4 is 1. So total decoders required will be 4 plus 1, that is 5, right? 5 decoders will be required. But I wanted to show you how to arrange these 5 decoders. So new slide. In this way you can get the number of, but if someone asks you to show the arrangement, so how you'll show, you have, what you have is A, B, a 2 cross 4. Here you have enable, so here you will have D0, D1, D2 and D3. So this D0 goes to enable of one decoder which has input C and D, and here will be Y0, Y1, Y2, Y3. Then I have another decoder which has C and D. Here the enable will be this, and we have Y4, Y5, Y6, Y7. Then you have this. This is Y8, Y9, so on up to Y11. This is C and D input. Then we have finally C comma D. So you have y12, 13, 14, and 15. So these are your outputs from 0 to 15. The inputs are A, B here, and these are all 2 cross 4 decoders. Then they are CD. So what is this means? So when enable is high, that is E, 0 0, this will get selected and it will be enable of this thing. And then when again C and D are 0, so this will be high, so that means Y0. And then D is 1, so Y1, and so on. You have a 4 cross 16 decoder. So any doubts in this question? Now moving forward to question number 8. You need to find the accessory code of the following decimal numbers. So find the accessory code of following decimal number. So how will you do it? You'll just write first, take this decimal number 24, write its BCD 8421 representation, that is 0010 and 10100, and you let 3 to both of them, 0011. So what you will have is 10 will be 1, 10 will be 1, then 1 will be here, and then 0, here it will be 1, it will be 1 plus 1 is 1 plus 1 is how much is 2, so it will be 0 1, then 1 0 1. So this is a accessory representation of 24. Then 658's accessory representation can be written as, you write the BCD of 658, so 0 1 1 0, 0 1 0 1, 1 0 0 0, then you will add 3 to it, 0 0 1 1, 0 0 1 1, and 0 0 1 1. So it will be 1 1 0 1, 1 1 1 0. So am I missing something? Okay, 1 plus 1. Okay, sorry. 1 plus 1 is 0. Then 1 plus 1 is 0. It will be 1. 1 plus 1 is 0. And then it will be 1. And finally 1. 1 plus 1 is 0. Then 1. 1 plus 1 is 0. Then 1. 0 0 1. 1 1 0 1 0 0 1 0 1 1. This is the axis 3. And this is the axis 3 of 24. If you directly want to write XS3 from decimal without conversion to BCD first, what you will do, take 2, add 3 to it, add 3 to individual decimal digits. 2 plus 3 is 5 and 4 plus 3 is 7. Then write the BCD of it. So it is 0 1 0 1 and this is 1 0 1 1 1. So as you can see, 0 1 0 1 0 1 1 1, and similarly for this, that is 9 8 11, as you can see here. So any doubts in this question? Now moving forward to question number 9 of today's live session. Just a second. So the question number 9 asks us, find the Boolean expression. Sorry, implement the Boolean expression f of summation f of abc equal to sum of minterms 2 3 6 7 using a multiplexer. So we have a 3 variable Boolean function and we need to implement using a multiplexer. So here it is not given whether we want to implement it using a 8 is to 1 mux or 4 is to 1 mux. So but let's just assume for the sake of sanity here, we will assume it using 8 is to 1 mux. So a three variable function, so an n variable, so an n variable function can be implemented by 2 raised to power n is to 1 mux, where 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 the n variables are used as select lines, right? This is one way. Another way is you can implement an n variable function using a 2 raised to power n minus 1 mux. So you can implement an n variable function by using a 2 raised to power n minus 1 is to 1 mux, where n minus 1 variables, input variables, are your select lines, and one of the input is applied to a input variable, to the input pins of the, based on the combination of the function, is applied to the input pins. So this is the one thing. Now we have to implement f of ABC using a 8 is to 1 mux, let's just say. So we have 8 is to 1 mux, so that is 2 raised to power 3. So my inputs are A, B, C, and now I need to input, here are is my input pins I0, I1, I2, so on up to I7. Now I need to give the logic to these, whether I need to put pin to 0 or 1 for the following function. So what I will do, I0 will be simply A bar, B bar, C bar, I1 will be A, B, C bar. So this is min terms. So these are simply min terms, M0, M1, so on up to M7. So my final expression is M is equal to M2 plus M3 plus M3 plus M6 plus M7. So all of the terms that are I0, I1 and so on are 0. So that is I0 will be connected to 0, I1 will be connected to 0, then I2 will be connected to 1, I4 will be connected to 0, I5 will be connected to 0, I6 will be connected to 1, and I7 will be connected to 1. So I write down here I0, I1, I4 and I5 are 0, and I2 equal to I3 equal to I6 equal to I7 is equal to 1. So in this way you can implement the following function that was given using a 8 is to 1 mux. Right? So was this question clear to you guys? And the theory that I gave into the this question, was it clear? So if that was clear, now let me just show the next question. So the next question asks us, implement f of ABC, so f of ABC equal to sum of minterms 0, 2, 5, 6 using a 4:1 mux. So here I have three variables. So if I wanted to use all of them as select line, I needed 8 is to 1 mux. But I have 4 is to 1 mux available with me. So that implies two of the inputs will be my select lines and one will be applied to the input of the mux. So I have f of ABC where A is my MSB and B and C are my LSB. So what I will do, I'll put B comma C, that are the LSB and the B term, that is a bit adjacent to the LSB. These I'll put as the select lines, that is S1 and S0. So B will be S1 and C will be S0. And my input A will be applied to the input pins of the mux. Right? So how to get the configuration for the input pins, so I'll draw implication table for that. Here I will have A bar, here I'll have A0. I'll draw an implication table. So here is this. So this is for I0, this is for I1, this is for I2, and this is for I3, right? So here is the minterm 0, 1, 2, 3. Then I have 4, 5, 6, and 7. So all those minterms that are high, that means that are given in the function 0 to 5, 6, I will circle them. So 0, 2, 5, and 6. Now I'll write the output. So this circular term is corresponding to A bar, so I'll write here as A bar. This circular term is corresponding to A, so I'll write here. This circular term is corresponding to both of them, A bar and A, so it's 1. And I have none of the circular term, so I'll encircle term, sorry, encircle term, so it's 0. So the function that is to be implemented can be done by this. So I have this 4 is to 1 mux. So this is my I0, this is my I1, this is my I2, and this is my I3. And these are my select lines B and C. So that is S1 and S0. This is my output F. Now how will I get output F? When I0 is connected to A bar. So let me just have this signal A from here and its complement here. So A0, and I1 is connected to A, so I1 is connected to A. I2 is 1, so this will be 1, and I3 is grounded, that is 0. So in this way, I can implement a function f of ABC, summation of minterms 0 to 5, 6, using a 4 is to 1 mux, where I0 was connected, where B and C are your select lines, and A is your input to the mux. So someone has written how 4 is to 1 mux. So I don't know what do you mean by this question. Can you please explain me, or can you just how, or is it clear? Let me just first ask this. Whether the doubt is clear or you still have any doubt, please ask me. And you can type in, you can unmute yourself, whatever will be comfortable for you. Please ask. Okay. So this was question number 10. So any other student having any other doubts? Okay, I hope there are no doubts. If there are any doubts, please ask me. So now let's just move to question number 11. So I'd like you guys to do this question first. It will hardly take 2 to 3 minutes. I will give you 2 to 3 minutes and then I'll show the solution. How many 2 is to 1 mux are required to implement 16 is to 1 mux? Here are your options and you need to tell me how many 2 is to 1 mux. Sir, explain us 2 raised power n is to 1 implementation. So can you please ask me? I am not able to get your doubt. Yeah, yeah. So in that, yeah, the question. So actually, yeah, let me just show you. Can you please? Okay, thank you. So let me just show. So here, I showed three variable system using 2 raised power n is to 1 mux. So I had three variables that are a, b, c. So 2 raised power 3 is 8. So I showed a function of three variables using 8 is to 1 mux, right? Then again I have here three variables, right? And that three variables is 2 raised power 3 is to 1 is equal to 8, but I have to implement it using 4 is to 1 mux. So when I have to implement this 2 raised power 3 is 8. So 2 raised power 3 minus 1 is 2 raised power 4. So I need to implement it using 4 is to 1 mux. So here two of my n, that is n minus 1. N minus 1 is 3 minus 1. Two are my select lines, two input B and C are my select lines. And one of the inputs, that is A, is my input to the mux. So as you can see here, I implemented a three variable system using a 8 is to 1 mux, and I implemented a three variable system using a 4 is to 1 mux. So I hope the doubt got clear, or was there any other doubt? Was it your doubt, or did you have something different? Your doubt was something different. Yes, yes, is true. Yes, is yes, exactly. Yes, yes. So 2 raised power n, let's just say we take n equal to 3. So 2 raised power n is to 1 is equal to 8 is to 1 mux. So here all of my three inputs are select lines. And then I have 2 raised power n minus is to 1 mux, that is 4 is to 1 for a three variable system, 4 is to 1 mux. Two are my select lines and one is my input. So I have shown both of them simultaneously. You got it? So let's just say I have a four variable system, right? I have let's just assume I have a four variable system. I have one example in the next slide. You can get that. I have a four variable system. I can implement it using 16 is to 1 mux with all the four variables as my select lines and input accordingly. And then I can also implement this 4 is to 4 variable system using 8 is to 1 mux, where three of my inputs will be select lines and one of the inputs will be my input pins accordingly to the input of the 8 is to 1 mux. Now here we have question number 11. So you need to implement 2 is to 1 mux. You need to implement 16 is to 1 mux using how many 16 is to 1 2 is to 1 mux are required to implement 16 is to 1 mux. You have a couple of minutes, then I can show you the solution. So I can see some of you guys have done this question. Let me just show the solution first. So you are required to implement 16 to 1 mux using 4 to 1 mux. So this can be done even. So if you have n cross 1 mux and you need to implement m cross 1, you can do it by this m by n, call it k1, then k1 by n, call it k2, so on up to its 1, and then the number of muxes required will be summation of k's. So here I need to implement 16 to 1 mux using 2 is to 1. So this is 16 by 2, that is 8. This is 8 by 2, that is 4. This is 4 by 2, that is 2. This is 2 by 2, that is 1. So these are my k's. That is 8 plus 4, 4 plus 2, 2 plus 1. That is 4 plus 2 is 6, 6 plus 1 is 9, 9 plus 8 plus 4, 4 plus 2, 2 plus 1, 8 plus 7, that is 15. Option A. Now question number uh, 12 of today's live session. I have here the following circuit which has 2 is to 1 mux. So here there are two is to 1 mux, and you need to find the output F. So what we'll do here, I'll just call it as output 1. Just call it as output 1 and F is as it is. So first I'll write output 1. So output 1 I can write as. So let me just first write the general form of 2 is to 1 mux. So it's S bar I0 plus S I1. So output 1 will be equal to S bar, that is X bar, and I0, that is Y, plus X times 0, because I1 is 0. So output 1 will be simply equal to X bar Y. Then my F will be equal to Z bar I0 plus Z I1. So F will be equal to Z bar. My I0 is output 1, that is X bar Y, plus Z times I1. I1 is complement of the output 1. So that is X bar Y whole bar. So my F will be equal to X bar Y Z bar plus X plus Y bar X plus Y bar times Z. So I use the De Morgan's law here. So F will be equal to X bar Y Z bar plus XZ plus Y bar Z. This is your answer, X bar Y bar Z bar X bar Y bar Z bar plus XZ plus Y bar Z. So that is option A. This is your correct answer. Now I have question number 13 here. So I would like you guys to do this first. This is done along the same lines as you have done for 3 variable system, and now you have to do it for 4 variable systems. So what I will do here, so it will be difficult for me to ask the answer to this question in a live session. So what I will do here is I'll just ask you what will be the value of what will be the value of A, that is what will be the value of I2 or two pins. What will be the value of I2, I3 and I4, 3 pins, sorry. What will be the value of 3 pins I2, I3, I4 to implement the following function f of A, B, C, D, and you have to use B, C, D as your select lines and A as your input to the mux for a 8 is to 1 mux. So I will repeat the question again. You have to implement the following function using 8 is to 1 mux. 3 will be your select lines B, C, D, and A will be the input to the mux. I am asking you what will be the value for I2, I3 and I4. 3 values. I'll just give you 5 minutes. It will take some time. I'll give you 5 minutes and please write down your solution. I2, I3, I4. One of the student has written down his answer. Has anyone else done it? So you need to report what will be the value of I2, I3, I4. A is your MSB, which is input to the marks, and B, C, D are input to the are your select lines. Your answer is almost correct. Check the first I0. Just check I0. Apart from that, I2 to I7 are correct. I0, check I0 again. I2, 3, 4, 5, 6, 7 are correct. I0 is incorrect. I0 should be 1. So now let me just show the solution to this question. So what I have here is I have four variable function that I need to implement using 8:1 mux. So as I already told you, this four variable function can be implemented by 16:1 mux, and where all the four inputs will be the select lines, and it can be implemented using 8:1 mux, where three of the inputs are my select lines and one of the input is my input to the mux. So what I will have here is B, C, D as my select lines, S2, S1 and S0, right? And input A to input the mux. So I will draw an implication table for this thing. So this will be A bar and this will be A. This is I0, I1, I2, I3, I4, I5, I6, I7. So this is I0. Sometimes it's also called a D0. So but I3, I4, I5, I6, I7. So here I'll write the midterm 0, 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14, and 15, right? Now I'll encircle all those terms that are present in the function. So 0, 1, 5, 6, 8, 10, 12, 15, right? I've encircled all those terms. Now I'll examine each of the column. So here both of the terms are encircled, so it will be 1. I1 only first term is encircled, so it will be A bar. Then second term in third column A. Here none of them 0. Then A, then A bar, then A and A bar, sorry, A bar and finally A. So if I had to draw the circuit for it, this schematic. So B, C, D are my select lines. B, C, D. This is I0, that is 1. This is I0, that is A bar. Then it is A, then it is 0, then it is A, then it is A bar, then it is A bar again, and finally A. and this is your F. So in this way, you could have implemented the function using the 8:1 mux. Now towards the next question, how many 3 is to 8 line decoders with enable output are needed to construct 6 is to 64 line decoders without any using any other logic gates? So we have done these types of questions earlier as well. So we have here as n cross m1 times n2 cross m2. So we'll take this term and divide by this term. Then the result of this division will be divided by n1 again till we get 1 and 0. So that is summation of k's that we have been doing all along. So we have 64 divided by 8, that is 8. Then 8 divided by 8, that is 1. So summation of k's will be 8 plus 1, that is equal to 9. That is option C. Any doubts? Now towards question number 15. How many select lines are required in 1 is to n demux? So the question asks us find the number of select lines in 1 is to n demux. So you know that 1 is to n demux, right? Let's just say the number of select lines that 1 is to demux require is m, and then that implies 2 raised to power m is equal to n, because the number of inputs is simply 2 raised to power number of outputs here because of demux. So number of outputs is simply 2 raised to power the number of select lines, and n is your input. N is your number of outputs. So that implies m. So what I have called m here is my number of select lines. So total input output, that is n, is equal to 2 raised to power m, and then that implies m is equal to log 2 of n. So the number of select lines will simply be equal to log to the base 2 of n, that is the number of output lines. That is option C is your correct answer. So any doubts in this question? So if there are no doubts, we can move forward to question number 16. So I would like you guys to do this question first. So you need to find out the BCD equivalent of 345. So I'll just repeat, you need to find out the BCD equivalent of 345, and these are your options. I'll just wait for 3-4 minutes. I'll take a short break and then I'll show the solution. So now let me just show the solution. And this was a pretty easy question. Most of you have done it. So this question states that find the BCD equivalent of 3, 4, 5. So we'll write the 8421 equivalent of the each of the decimal digit. So 3 is written as 0011. 4 is written as 0100. 5 is written as 0101. So this is 3, this is 5, this is 4 and 3. So this is the 3, 4, 5. That is option D. Now we have another question along these lines as well. So the number 762 in decimal would be represented in 8421 code or BCD code as, so 7, I'll take 7 and write its BCD equivalent, that is 0111. Then 6 I'll write as 0110, and then 2 I can write as 001110. So my final number will be 011 0110 0010. That is option C. Now towards question number 18 of today's live session. I would like you guys to do this question first, and then I'll show the solution to this question. So the question states that consider the output A and B with I0, I1, I2 as input and A and B as output, and A is given by I2 plus I3, B is given by I2 bar I1 plus I3. The above circuit is, so you have four options and you need to tell what does the above circuit do. Sorry, what does the above operation do? So you have two expressions and you need to tell which is the what is the following circuit. So let me just repeat the question again. Consider the output A and B with I0, I1, I2 and I3 as inputs and A and B as output. So output A is given by I2 plus I3, output B is given by I2 bar I1 plus I3. You need to tell what is the above circuit. So options are 4 is to 1 mux, demux, BCD circuit and a priority encoder. Now let me just show you the solution. So as some of you have written, this is right as this is a priority encoder. So demux and mux, you guys have seen it, and you just by looking at the expression itself, you can just say this is a priority encoder. Now let me just show the elaborative solution. So this I2 plus I3 means if one of the I2 or I3 is 1, A will be 1, and the expression B is also says that if I3 is 1, it will be 1. So 1 1 will be when I3 is 1. It will be always 1 when I3, it will be always 1 1 for I3 equal to 1. So that means whenever I3 is 1, my output will be 1 1. So in that way, loosely you could have gotten it is a priority encoder. But to examine it, let's just draw the truth table of priority encoder. So this is the truth table of your priority encoder. You have four inputs I3, I2, I3, I2, I1, I0, and your outputs A and B. So for I3, I2, I1 equal to 0, 0, we have don't care condition of A and B. Now I3, I2, I1, I0. So when I0 equal to 1, my output is 0. That is 0, 0. When I1 is 1, so I don't care about what is I0. So my output will be 0, 1. So for both of them cases, my output will be 0, 1. When I2 is 1, so when I2 is 1, regardless of what is the input at I1, I0, my output will be 1, 0. So here are the four cases, here to here. And then when I3 is equal to 1, whatever will be the inputs at I2, I1, I0, my output will be 1, 1. So that is 3. And if you can draw the K map of the following, you have K map for A. So here I have I2, I3, and here I have I1, I0. So it will be something like this: 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So you can draw a core this octet like this and an octet like this, and A will be equal to I2 plus I3, and for B you can have a K map like this. You can cross check these with the truth table. Yes, in the interest of time, I'm not going into details, but you people are well versed with K map, so I just assume you guys know this. And this is your B, and here you have I3, I2, here you have I1, I0, and you have something like this: 1, 1, 1, 1, 1, 1, 1, 1, and 1, 1. You can draw a octet like this and a chord like this, and your B will be equal to I2 complement I1 plus I3. So both of them are the required expressions, and the option is correct option is option D. Any doubts? Now let's move forward to question number this was 18, 19 of today's live session. So determine the function performed in the following combinational circuit given in the figure. So what we have here is we have three 2:1 mux, and you need to determine what is the functionality of the following mux. So when three 2:1 mux are connected like this is simply your 4:1 mux. You can also verify it like this. So if you want to implement 4:1 mux by 2:1 mux, you will do that this 4:1 by is equal to 2, 2 is by 2 is equal to 1. So you need 3 muxes, and these are your 3 muxes, and it is a 4:1 mux. Because 8:1 mux, 16:1 mux, and 32:1 mux cannot be implemented by. So see, let me just show you why I have shown the solution like this only, without going for the output expressions and all. So what are your options? So this is how you approach in MCQs, where the times are where time you want to constrain time, where you want to sort your time accordingly. You want to give very less time to the easy questions, and for difficult and more intensive questions you want to give more time. So here examine options also. Whenever you are appearing for MCQ type questions, examine MCQs also, your options also. So here you are giving 3 2:1 marks, and the options are 4, 8, 16, 32, right? So 8, 16, 32 cannot be implemented by 3 2:1 muxes. So only option that is left is 1, that is option A, 4:1 mux. You can solve it also by writing the individual expressions, but here you don't need to do like that. So that is option A. So option A is your correct answer. Any doubts in this question? Uh, Your voice is breaking, or some kind of noise is coming out from your microphone. Yeah, yeah. I'm just this. So I'm just showing the solution right now. So let me just complete this first. So first of all, I told you whenever you have doubts, ask at the end, and this is not pertaining to this lecture. So you could have asked it at the end. Lecture is not finished. So why are you hesitant to ask it right now? I told you any doubts you can ask it at the end, and this is not pertaining to this lecture. So let's just wait at the end and discuss at the end. So this was your question number 19. Now going to question number 20. So question number 20, I would like you guys to do first, and then I'll show the solution. What should be the value of D0, D1, D7 so that the minimized output of F equal to A, B plus C. So you have a function F equal to A, B plus C. You need to implement by the following circuit. So what should be the value of D0 to D7? It might take some time, so I'll give you 5 minutes and then I'll show the solution. So has anyone done this question or doing? Please confirm if anyone is doing so I can wait for 2 3 minutes. Okay, so I'll just wait for a couple of minutes. The reason why I gave this question to you because I wanted to see the approach you will take. So there are two approaches with which you can solve this. One will hardly take 1 minute and one will take more than 5 minutes. That's why I have kept it here. And to Mr. Mishra, if this is the question from assignment, I can't discuss it. If it is from this year's assignment, I can't discuss it. If you would have already gotten solutions for the assignment, if it's current assignment, I can't discuss it. If it's a solution, sorry, if it is a question of this year's assignment, I can't discuss. And if the assignment deadline is already passed, you guys will have the solution. You can refer to the solution. You can check it there. So I'll just wait for 1 more minute and then we can solve it. This is an interesting question. It's pretty simple if you take one way, and it becomes cumbersome if you take another way. But you can get the solution both ways. So let me just show the solution. So before I show the solution, I have one question. Actually, we can solve it two ways. So let me just show you the one way, then we can solve it another way. So let's just solve it. So I'll use my keyboard this time because I have to write many expressions. So I'll write down the expressions here. So these are your 2:1 mux. These you can easily find that these are your 2:1 muxes. So let me just draw this. I will call as x1, this x2, this x3, this x4, this x5, this x6. This is the elaborative way that I was talking about. So this is the way that you could have solved it. So your x1 is equal to your x1 is a 2:1 mux and C is your select line. So x1 is equal to, so this is C bar D0, C bar D0 plus C D1, right? This is your x1. Then your x2 is, then your x2 will be equal to again C bar D2 plus C bar D3. So let me just copy this thing. Then then x4 and then x4. Yeah. So your x3 will be equal to, just a second. Let me just put them correctly. So this will be D4, this will be D5, this will be D7, and this will be D6, right? C bar D4, C bar D5, C bar D6, C D7. So these are your x1, x2, x3, x4, right? Now your x5 will be equal to your x5 will be equal to so x5 is equal to b bar x1 plus b x2, right? This is your x1 b bar x1 plus b bar x2, and your x6 similarly will be equal to b bar x3 plus b x4, right? Now x5 can be written as x5 can be written as so b bar as it is x1. So let's just put the value of x1 here. Then put b and put the value of x2 here. Now for x6, something happened to this. For x6 will be equal to b bar, put the value of x3 here, and put the value of x4 here. Now when you expand them, your x5 will be equal to b bar c bar d0 plus b bar c d1 plus b c bar d2 plus b c d3. You can check this. And similarly, your x6 will be equal to b bar c bar d4 plus b bar c d5 plus b c bar d6 plus b c d7. And your final output f will be equal to a b c will be equal to a bar x5 plus a x6. That is also good because this is also your 2:1 mux. And when you expand this, this is equal to, I will just write the whole thing. This is equal to basically, is equal to a bar, b bar, c bar, d0 plus A bar B bar C D1 plus A bar B A bar B C. So then it will be A bar B bar C. Then it will be A B C bar D3 plus A bar B C D4. And it will be A B bar C bar. Then it will be D5. Then it will be so no, it will not be B5. This is D0, D1, D2, D3. This will be D4. Then I have A B bar C, that will be D5. Then I have A B C, that is A B C bar, that is D6. Then I have A B C D7. And this simply, then I have, let me just draw for that. So this is the function I got, the function value I got. Now f, the required function I need to implement, f required is f is equal to a of b plus c, a times b plus c, that is equal to ab plus ac. And in terms of minterms, if you have to write it, you can write it like this: a b c plus a b c bar plus a b c again, so I don't need to write it again, so a b bar c. So that is summation of minterms 5, 6, 7. And if you carefully look at these things, this is min 0, m1, m2, m3, m4, m5, m6, m7. Only m5, m6 and m7 are 1. So that means d6, d5, d6, d7 are 1, and all other d's d0 to d1 are 0. So my correct option is 0, 0, 0, 0, 1, 1, 1, 1. So this was your one way of looking at the answer question. Yeah, one of the student has done it correctly. So other way which would have saved you a lot of time is look at the figure itself, circuit itself. What is it? You have three variable system and three variables are your three select lines, and you are using six, sorry, 4 plus 2 is 6, 7, 7 2 is to 1 mux. So when you use 7 2 is to 1 mux like this, you use 7 2 is to 1 mux like this when you want to construct a 8 is to 1 mux. So this whole thing, where is it? This whole thing is your 8 is to 1 mux. These are your input to the mux of 8 is to 1. These are your three select lines. So what you needed was you had three select lines as your input variables and you have the muxes. So you need to just implement the function sum of minterms 5, 6, 7 using a 8 is to 1 mux. So you can implement it by having 5, 6, 7 connected to 1 and all other data bits connected, these input bits connected to 0. So did you get it? And that's nice. Now, towards the last question of today's live session, determine the inputs of the given 4 is to 1 mux to make the output Q equal to xy plus z, where x is your MSB and z is your LSB. Use x and y your select lines and z your input variable. So that is input to the mux. So two more things that are different from what we have done earlier. Q is equal to xy plus z. So this is our output. Let's just write it in the standard POS form, sum of products SOP form. This is xyz plus xyz bar. Then you have x bar y, sorry, x bar z plus xz. Then you have equal to, this is equal to xyz plus xyz bar plus x bar z, x bar yz plus x bar y bar z plus x bar y z plus xy bar z plus xyz you can cross check it, and this thing is equal to sum of minterms 1 3 5 6 7. This is equal to sum of minterms 1 3 5 6 7. This you can cross check. So you need to convert this to SOP form and then write the thing 1 3 5 6 7. I have done it quickly, but I guess you guys got the idea. So what is the thing that we have done different here? The question asks us to do differently from what we have done earlier. So here we need to implement a three variable system using 4:1 mux. So two input will go as my select lines and one will be go to the input to the mux. So the question asks us x and y are your MSB. So x is your MSB and z is your LSB. X and y are select lines and z, that is the LSB, is your input line. So x and y, so this is x and y, and now I need to figure out for z. So this is z bar and this is z. So again, as I have done it earlier, so I'll write d0, d1. In place of I0, we used to write I0. Here we have d0, d1, d2, and d3. So here I will write 0. So can anyone tell me what should I write here under d1? So what should I write here? No. So this is the catch. So in the previous implementation, what were we using doing? F of ABC, or let's say f of xyz. So yz, that is your LSBs, were to your select lines, right? A, B, C, B and C were your select lines. A, which was your MSB, was the input variable. So that time this was 1. But since it is Z, it is your LSB. So here 1 will come here. And then 2 here, 3 here, 4 here, 5 here, 6 here, 7 here. Right? And now the procedure is same. Enclose the encircle the these minterms that are present in the function 0 1 3 5 6 7, and then d0 will be z, d1 will be z, d2 will be z, and d3 will be 1. So z z z 1. So option A is your right answer. You got my point? Z was your LSB, and your LSB is connected to your input. Their way, when we did that implementation, their MSB was connected to your inputs, not LSB. So that's the difference. So in the implementation table, you need to change the format 0 1, because if you look at the truth table of ABC for a three variable system, A remains 0 0 0 for first four cases, then it is 1 1 1 for all four cases. That's why 0 1 2 3 comes in Z bar line or A bar line, and 4 5 6 7 comes in the 4 5 6 7 comes in the second line. Here you have a LSB. It changes from 0 to 1, 0 to 1, 0 to 1, 0 to 1. That is 0 will be 0, then will be 1, then will be 2, then will be 3. So in 2 Z bar is 0, in 3 Z bar Z is there. So that's why 0 1 2 3 4 5 6 7. And when it's the MSB, you write 0 1 2 3 4, 0 1 2 3 4 5 6 7. I hope you got my point. So keep this thing in mind, because last year I remember I was also a course TA for this course. One of the student, we did examples like this, as you saw earlier, f of ABC, where A is your MSB and is connected to the select line, and B, sorry, to the input, and B and C are your select lines. But the question was showing LSB connected to your what should I say? LSB connected to your input variable of the mux, and A and B, which are A where A is the MSB, were connected to the select lines. So in that way, your what should I say, your implementation table implementation differs from that case. So examine those things, which is your MSB, where this MSB connected, where are the select lines connected. In elaborative way, that time the question was given as a mux and you need to find the output. Using elaborative method, it will take 4 5 minutes. You could have gotten the right answer even if you were not having any clue about the implementation at all. But the moment you want to construct using implementation table, keep these things in mind. So that was all for today's live session. We'll meet next Sunday from 3 to 5 p.m. and we'll discuss questions related to week 6. Thank you. Thank you for joining. Any doubts, by the way, in this question? If not, we can close the session. So thank you for joining. See you next week. Thank you.